for the few minutes delay. As you probably can already figure out, this talk will be about word embeddings for specific domains. Let's dive right in. Why do we need word embeddings for specific domains? Well, there are really great word embeddings or models to generate word embeddings, but they are generated on corpora that are as large as possible. So they cover every domain possible. You got two problems, two main problems. And the first is words are ambiguous, meaning that they have multiple meanings. And for a domain, in a specific domain, you might only be interested in one of those senses, one of those meanings of those words. So how can you push those word vectors towards that meaning or extract that meaning? And the second major problem is that you usually have a terminology in your specific domain, meaning that you have terms that if you use a general word corpus and look at the most frequently used words and base your vocabulary on that, you miss those domain-specific terms. And to explain a bit more about the context of this question, like why this is important, and also to explain the short answer or the problems that I just sketched, let's start by covering the very basics of word embeddings. So this talk is meant for people that just started in natural language processing, figured out that there are a lot of tutorials to get started with word embeddings, but now want to use it on their own projects and specifically on their domain. So in order to, what we need to cover the basics are basically the concept of what are words and how can we represent them for the computer. So let's start slowly. First, a little bit about myself. My name is Jetze Schuurmans. I'm a master's student of econometrics at the Erasmus University in Rotterdam. About half a year ago, I started exploring the world of natural language processing, and I chose to write my thesis on intent classification in dialogue systems. So now I'm also really working with natural language processing problems. And a bit before that, I got introduced to Python, and I noticed that Python is a really cool tool for working with natural language processing, mainly because it has a great community and there are great open source resources that you can use. So this slide is also a little bit of disclaimer. The methods that I propose here are merely a suggestion for you to try out. By no means are they the best possible way to deal with domain-specific problems, mainly because, well, every domain has its own caveats. So this is just the first thing and a really easy thing that you can try out and might actually already be helpful. And then further on in the presentation, I'll also talk a little bit about what the limitations of this very, very naive method is and how you can basically work around those and try those for your domain. So let's start with the basics. So words are basically a symbolic representation for us humans. With a word, we refer to some concept or something. And in order to represent them for the computer, of course, we need to convert them to numbers. As you probably know, you can do that with one-hot encodings, but then you end up with a huge matrix, which is just as large as your vocabulary. That just gets out of hand real quick. So a better option is to use dense representations, meaning that you take a smaller vector, let's say 50 to about 300 dimensional vector, and with that vector, you try to represent that word. And usually that word is then represented, or the meaning of that word is represented in that vector space. And why you would want to use dense vectors as opposed to one-hot encodings is mainly because of the generalization of your model. If you use a neural network architecture and you're using one-hot encodings, the next layers after the features will actually represent dense vectors. So you're almost doing the same thing if you're applying it in a neural network architecture. But the main problem is that you are training those representations only on the words that occur in your training data. And with dense representations, you can train those on unlabeled data. So before I was referring to the training when you actually are using, for example, text classification. You have text, you have the labels, and you're training your model to make a meaning of that word that's relevant for your application. And the training for dense vectors can be done on unsupervised in an unsupervised way because you don't need to label text in order to input it into the training algorithm. So when will you be using word representations or dense representations in your in NLP tasks? So first, when you get text as an input, you'll start with tokenizing it, meaning that every word gets represented by a number, and then that number is basically the input, or the sort of maps your to the words, and then after that, you already have the morphological analysis. You can already use word embeddings in your morphological analysis. So if you take, if you split a word into a prefix and a suffix, or take that out of the stem of the word, and then you train word representations for the prefix, the stem, and the suffix, then you can already use word embeddings in there. So very early on in any NLP task, you'll deal with word embeddings. So little bit of history about dense word representations. It started earlier than many people think. Already in 1986, Rumelhart was learning word representations using the backpropagation methods. And then in 1992 and 97, they started working with continuous space vectors. But only after 2003, when Bengio used neural architectures for NLP tasks, they became really popular. And then especially the last few years, since 2013 and up until now, you got great general trained word vectors on large corpora. So who here knows to what type of word representation I'm referring to when I'm talking about the method proposed in 2013 by Mikolov? Here in the front was first, I think. What type was it?
fastText with subword embeddings?
Word2Vec.
Okay.
fastText was in 2016 by Jolien Graaf and others. And then in the middle, in 2014, Pennington and Socher and Manning came up with Glove. So these are the three previous methods that I mentioned before are mainly different kinds, not only in the sense that they well, it's a different method, so there's a different idea behind it. The very early ones before were based on were count-based methods. So what you used is you would go over the whole corpus, you count all the words, and you count all. Basically, you get all the statistics from how words appear in your corpus, and based on that, you either apply LDA or PCA or another method, and from those statistics about word occurrences and co-occurrences, you base representations. And then after that, they started with direct predictions, and in direct prediction, prediction methods, you also look at how words co-occur. So what are the contexts that words appear in? But you're using more. You're using a predictive method, for example, skipgram or continuous bag of words. And these are examples. For example, word to vec uses a scriptgram and a continuous bag of word method. fastText also uses that, but uses more neural network architecture. And then there are, of course, with direct methods, it scales bad with your corpus, and if you want to add more add words or text to your corpus, then that's a bit harder to do. But the upside is that you can also capture representations that go beyond co-occurrence and similarity. Then the sorry, that was for the direct predictions. The count-based methods are faster to train, of course, because you only have to go through the corpus one time, and because they make a more efficient use of the statistics. But then the downside of the count-based methods is that they only take into account the word similarity, so and not really the direct prediction methods take more the meaning of the word into account. But then you can also so what Paddington, Stocher and Manning did was try to combine the best of both worlds and create GLOV, which which is faster to train. It scales better to huge corpora. It's also better when you're working with smaller corpora, so that's also why we'll be using it later on. And well, these type of methods are trained on general corpora, so I'll call them generally trained methods. And the problem is that, first of all, like I mentioned, words are ambiguous, so they have multiple meanings. What Aurora actually showed was something pretty neat, that if you have a word which has multiple senses, but you don't distinguish between the different meanings of the word, so you create for one word has, let's say, 3 senses, in other words, meanings, and you only use one representation, then that one representation is basically a superposition of all those 3 individual senses. So if you would train the same algorithm on the same corpus, but then distinguish for that single word when it's when the different meanings actually when it's referred to the different meaning, then those 3 different meanings would create 3 different points, and then what you could also do is, if you only have that generally trained word or representation of a word, you still have that corpus around, you could actually extract the different senses of the words, and so only given your corpus, the algorithm that you use, and the trained word vectors, you could extract multiple the different senses that one representation has, and that those different senses still need some human interpretation. You will only get different words that it's likely to co-occur with, but for humans it's pretty easy to extract the meaning or the general sense that is referred to. But the downside is, of course, that you need human input. So for every time you do this, you need to look at, okay, which word is it? How many senses does it have? You need an intuition for that. And then after you get the output for the model, you need to make the final call on what the actual sense is, like what is the actual context, based on those words that it gives as examples. And then the other problem is domain-specific terminology. This is a problem because if this term falls out of basically the vocabulary that you're using, you'll use that in your model with a random initialization for that vector, and surely we can do better than random. And mainly because if you you could retrain that model. So if you have this random initialization for a word that you want to add to your vocabulary because it's important to your domain, then you would either need a large data set, and with a large data set, I'm referring to a labeled data set that's about your let's say, task classification problem. But for that, you need, of course, lots of text and labeled text, and that last part is usually a bit of a problem. So what you can do if you have that, then you can train the word vectors just like a parameter in your model and tweak that. You can either, for some methods, it's even better to completely start with randomly initialized word vectors. For example, semantic analysis, because when you're talking about meaning of words, or sentiment analysis, sorry. With sentiment analysis, you're referring to the loading of a word and what effect it has on the sentiment, and not about the usually in word vectors, you're representing semantics, so the meaning of the word. What you could toy with is, or play with is, you could start with fixed vectors, and then later on in your final sets of epochs, you could then choose to only then choose to update your word embeddings. The upside of this is that when you start with your model and you initialize all the parameters of your model randomly, then it usually has large update steps. And if you use generally trained word embeddings, then you only want to tweak them towards your problem and not have in backpropagation mess up this beautiful representation that's already there. You only want to tweak them in the right direction. And you could do this by just starting with them fixed, and then later on also updating them. And the downside is that this is, of course, problem specific, so you would need to figure out yourself, like, when is the optimal point in your training where you make switch them from being fixed to setting them as a trainable parameter. But of course, we we not always have a large data set. So what if you have a limited number of observations, you might not want to train the word embeddings in your model, of course, because you're likely to overfit on that training set. So what you could do is either you fix them and use generally trained word embeddings, or create your own corpus based on a specific domain, and then retrain the word embeddings, and then use that as a start. So how can you get a domain-specific corpus? Well, of course, it's best if you would have if you're working on like, say, text classification, that you already have unlabeled text data on your specific domain laying around, or related topics describing basically on the topic of your problem. So, for example, for intent classification in dialogue systems, you might have a lot of customer interactions and already recorded those, or already have transcripts from those, and then but haven't labeled them yet. And you can still use that to retrain or train the corpus. And the upside of that is that it's in the writing style is the same as you would occur in the problem that you're facing. So that definitely has benefits. But the problem is that you usually don't have this data set laying around, or it's not easily accessible. So another way is just use Wikipedia, and it's very easy to just gather your own domain-specific corpus, and then either train word embeddings on that corpus, or take pre-trained word embeddings and then retraining them using that corpus. And what you could also do is, well, Wikipedia has its upside that it has a lot of different domains. So basically, for almost any domain, you could go to Wikipedia, find articles about it. And that would be a very easy starting point. But the problem is that usually another upside is that there are fewer typos and misspellings in Wikipedia text. But the downside is that well, it might not be the same writing style as you would occur in your problem. In the case of intent classification, you could go towards internet blogs and try to scrape those. The problem is, for every single domain, you would need to find the right blog for you. And if those blogs are, if you go from your first blog where you scrape this and then go to your second one, you need to go and have a look again whether you cleaned the data properly. And most likely the structure of the blog is slightly different, and you need to take account for that. So then for every single domain, you would need to create a separate scraper. So what I did, I would just looked at the Wikipedia pages. It's really easy to gather your own corpus from Wikipedia, because the neat thing is there already a Wikipedia API which you can call with Python, so you already get the content from Wikipedia pages in your environment, and then from there you just start off with initial page titles on your domain, and then from there you save the content, get the links, go to those pages, and then repeat it all over again. You save the content of those pages, get those links. The only thing that you need to take care of is keep a list of pages that you've already been to, because you don't want to visit one page twice, because then you'll adding the same text to the corpus which is already exactly in there, and you're not sure whether this is the right, whether this is a general page which you also want in your corpus, because you don't want to be only training domain-specific words, but also a general, in the case of intent classification in chatbots, you still want to have a normal conversation, but you do not want to basically overtrain on those pages, and you got the problem where you'll probably get stuck in loop if you do this for multiple loops. The upside of this method over the scraping blocks is that it's very easy to clean the data. You only need to remove a few special characters, actually one type only, and need to remove the page titles or the paragraph titles. But before you remove the paragraph titles, I would advise to remove the one of the last two paragraphs, because in those last two paragraphs there are only references, and those references are merely the text of those references, which are not useful for training because they're not complete sentences. And then you can already tokenize that corpus and then train your model. Training word embeddings is fairly easy. There are a lot of tutorials online already, so I won't go into much detail. What I used was, for GenSim, I used Word2Vec and fastText, and for Glove, there's a really neat Python wrapper already there on GitHub. So after you've created those domain-specific word embeddings, you want to check for whether how they're performing. So this is not fairly important, but I would still advise to have a look at it because it's pretty easy to set up. Is the intrinsic evaluation. These are usually word relations that either look at analogies and similarities between words, They are created for general purpose word embeddings, but you don't want to lose that general purpose. So the only thing that you need to keep in mind is that they're not looking at words which have a specific meaning in your context, because you retrained them and you want that special meaning. So you only need to check whether these are in these analogies, and maybe remove them or take into account when you got the performance that might be due to that. But most importantly is the external evaluation, where you just plug this into your model, use them as fixed vectors. Well, again, because I'm talking about a domain where you have limited labeled data, and then see how they perform on that task, and then go back and change a few things in the word embeddings, or try different types of algorithms, change hyperparameters around, and check what works best for your domain. So about the domain-specific problem, I was talking about, originally I wanted to do a different data set, but the problem there was that I had some practical issues and some legal issues. So I needed to switch to this data set, which is from a paper which evaluates intent classification, not only intent classification, but part of their papers about the performance of intent classification in a dialogue setting. And I use this as a little toy example. The downside of this toy example is that I can't really show that Wikipedia works well, because it's about Ask Ubuntu, and Ask Ubuntu, of course, it's way better if you try to scrape blogs about Ubuntu, because they are more towards the domain that you're working in. So because the performances with the generally pre-trained word embeddings were almost exactly the same as the domain-specific retrained word embeddings, I left those out of the presentation. And then, as a short summary, so what I would like you to take away for this is dense word representations are very powerful. Pre-trained, they're very good for general purposes, but you might want to look into making them domain-specific. Look out for the two caveats that I pointed out. So words are ambiguous, and you might only be interested in one of the meanings of that word. And the second one is the word. There may be words that are very important to your domain, but they're not in your standard vocabulary, so you might want to add them. A neat trick to check whether to get a short list of those words is just get different Wikipedia documents, because you already got them, imported them, and then look at TF-IDF, see how they rank among in the specific documents that are on your topic. And then you can already get a short list and see maybe there's some words that you haven't thought of yet that are still relevant for your application. So where to go from here? After the conference, I'll post the PyWiki domain scraper on GitHub, and with it the toy application, so you can also try it yourself. And from as a next step, besides the tweaks that I pointed out earlier, it's also good to look at the biasness of generally trained word embeddings, and there are already methods looking into how to remove this bias or how to cope with this bias. There's a cool article about in the MIT Technology Review, and I think it was PyData New York of a year ago, where Mike also addressed the prejudice in text data. I'll definitely recommend having a look at his video on YouTube. And well, with that, I'd like to thank you all for being here. Also thank the organizers. And if there are any questions, please let me know.